Okay, so I am very glad to introduce Nadya Gurevich from the Ben-Gurion University of the Negev and announce her talk on Gelfand-Graev representation for covering groups. Please.
Okay, thank you very much for invitation. It's my favorite seminar by far, and I'm glad to speak here. So I'm going to talk about the Gelfand-Graev representation for covering group, which is an ongoing project with Edmund Karasiewicz from UT and Fengao. So though the story mostly concerns covering groups, but I will start talking with a similar problem for linear groups. So let me first introduce some notation that all concern linear group. Okay, so let F be a local non-Archimedean field with a ring of integers O and the maximal ideal with a fixed uniformizer and the residue field of characteristic P. In this talk, G will be a group of F points of a split linear group, and it contains Borel with a decomposition in a torus and unipotent radical, and we use the notation B-op and T-op for the opposite Borel subgroup. Now W is the Weil group. The co-character lattice will be denoted by Y. It contains a root system, and which in turn contains a set of simple roots. Okay, now so that was all related to algebraic group. Now we fix a non-degenerate character of the opposite unipotent. Of course, we could use usual unipotent. It will be just more convenient to use the opposite. I will mention why. So this is a non-degenerate character of conductor P. The conductor is very important. This means that the restriction of psi onto every root subgroup intersecting compact subgroup is non-trivial, but the intersection on the root subgroup with a variable taken from maximal ideal is trivial. Okay, now for any algebraic group, we will denote by H lower bar the group of FQ points. So it will be a finite group. Okay. Now K is a maximal compact, and we have a projection from G of O, so that's this fixed maximal compact, and we have a projection to the group of FQ points, and as usual, quite standard, the Iwahori subgroup is the inverse image of the Borel. Okay, with this notation, we go on and define this, our main player, Gelfand-Graev representation, which is just a compact induction on G from opposite parabolics and a character. Okay, this is Gelfand-Graev representation. What's the significance of it? It contains every generic irreducible representation of G as a quotient. Okay, and indeed, if we take a representation pi tilde is its contragradient, then by duality, this home space is exactly the home space of pi inside big induction. And this space is not zero whenever pi is generic. Okay, but our goal will be to, we concern Iwahori-spherical representations. Okay, those representations, irreducible representation for which I fixed vectors, I is Iwahori subgroup, is not, this space is not zero. And whenever pi is an representation of G, it generated by its I fixed vectors. So there is equivalence of categories, and the space pi I is a module over the Iwahori-Hecke algebra. Here it appears, all the functions, the Iwahori-Hecke algebra is functions of compact support of G mod I from two sides under convolution. And we know that representation is generic if and only if it's a quotient, it's I fixed vector, it's quotient of VI. So our goal will be to understand VI as this module. Okay, so this is a well-known problem and solved long ago. But to introduce the solution, I will to give an answer. I first need to know a little bit about the structure of the Iwahori-Hecke algebra. So let me remind the Iwahori-Hecke algebra. It contains, first of all, finite Hecke algebra, which are just functions by I-invariant functions supported on K is G of O, which is isomorphic to the group algebra of the Weil group. Okay, it has a basis TW of characteristic functions of cosets. Now, inside this subalgebra, let us take two idempotents corresponding to the trivial and sign characters. So the group W has a trivial and sign character, and let E1 and E minus 1 will be associated idempotents. They will be used later. So another important subalgebra inside HI is a so-called Bernstein subalgebra, commutative algebra, which is isomorphic to the group algebra of co-character lattice. Okay, I'm not going to define it for positive with some basis parameterized by element of co-character lattice. For positive, for dominant co-characters, theta lambda are just characteristic functions of double cosets again. Okay, so it is known that as a vector space, HI is isomorphic to the tensor product of this finite Hecke algebra and this Bernstein subalgebra. Well, the product, the exact commutators, the relations between the product on the algebra on the right hand side, on the tensor product, is given by so-called Bernstein's relations. They're needed in work, but they're not needed in the talk. Okay, so another important piece of information is that when we average, so multiply the HI on the idempotence E1 on both sides, we're basically averaging over K on both sides and get the spherical Hecke algebra, which is by Satake isomorphism isomorphic to the group of group algebra of lattice of co-characters, COY, which is fixed by W. Okay, and we know that there is a so-called spectral basis in COYW, which is defined by traces of irreducible representations, and the corresponding basis on Hecke algebra will be denoted by A lambda. Lambda here goes over over dominant characters. So far, this all is about roughly structure of the Iwahori-Hecke algebra. So I remind that our goal was to describe VI, okay, as HI module. So here is a theorem. It has been known to experts a long time ago. I think it appeared in a paper of Chen and Savin rather recently, in the last 5 years. So there is a description of the space VI, I fixed vectors in the Gelfand-Graev representation, as a tensor product of HI with over subalgebra, the finite Hecke subalgebra, with a sign character of this subalgebra. So you can say that this is an ideal in HI generated by the idempotent E-1. It's just the same. Okay, and this isomorphism is realized by very concrete map. There is a so-called twisted Satake map, S psi, which is starting with a function on the Hecke algebra. You just average it on the left against psi to make it U psi invariant. Okay, so it belongs to VI now. Okay, and the theorem basically is determination of the kernel of this map S psi. Okay, note, but which is some it is important that the map S psi is surjective. Okay, this is true in the linear case. The analogous statement will no longer be true in the covering case. That's why I stress it now. Okay, so this theorem basically describes the space VI as HI module, and what we can do further, this is just a corollary, that we can further average both sides over the maximal compact K on the right. So here is a corollary. Assume that GB adjoint group, okay, so that the character R, which is half of sum of all roots, positive roots, belongs to the co-character Y. So this assumption is important for the need statement that appears below. In this case, when we, as I say, multiply both sides of the equality in the theorem by E1 on the right, we get isomorphism. We get that the K-fixed vectors in the Gelfand-Graev representation is a free module over HK of rank 1, and we can very explicitly describe the structure of this module. Precisely, there is a generator, special generator, corresponding to the weight rho. Basically, those elements phi lambda plus rho are all characteristic functions of corresponding torus elements. All right, all the functions in V are basically functions which are K invariant on the right and U psi invariant on the left. So they are determined by their values on the torus. And as I say, this phi lambda plus rho is just a characteristic function. And the structure of this model is very transparent in a sense. Starting with a base point phi rho, if we multiply it by an element of the spectral basis corresponding to the trace of irreducible representation v lambda, we just shift the weight by lambda. So by multiplying on this quite non-trivial element A lambda, we move from this basic point to another another characteristic functions of a different class. Okay, so this is very nice, especially because it gives a short proof of the Kasselman-Shalaika formula. Okay, which it's all real. Here. Yeah, so I remind we are still talking about linear groups, not covering groups. Okay, so basically, let me shortly describe how this statement, this corollary implies the Kasselman-Shalaika formula. So Kasselman-Shalaika formula is a formula for the values of the spherical Whittaker function. So I formulate the spherical Whittaker function as a map which has on G, which is K invariant on the right, U psi invariant on the left, and has values in COY. In this way, I'm talking about so-called universal spherical Whittaker function. So not a spherical Whittaker function defined on each induced unramified representation separately, but sort of looking at the family of them all. So let me introduce the notation. We consider the induced representation from U psi, K fixed vector on it. It is naturally a module over a spherical Hecke algebra. So, and COY, or another case, is also a module over the spherical Hecke algebra just by multiplication. So we know that HK is isomorphic to the W invariance polynomials on Y. Okay, so just by multiplication with a small twist, whose importance it's just there. I don't want to explain it now. We have an action of HK on COY also. So the spherical Whittaker function is basically kind of eigenfunction in this space. So it's an element in the tensor product over HK, where the action was described before. Okay, and whenever we have such a function, so this function is actually not unique, but it will be almost unique in this, as you will see in a minute. I mean, it is determined by its value on a single element. So say we have such a Whittaker function. Okay, the integration produces. Given an element in Gelfand-Graev representation, which I remind the function on compact support on G mod K mod U psi, and an element in WK, we can multiply those two functions and integrate them over U, and the result produces an element in COY. Okay, so now the theorem, which is basically Kasselman-Shalaika formula in its universal formulation, is that for any function, any spherical Whittaker function holds that whenever we fix the value of W at a point corresponding to the weight rho, okay, it automatically fixes the value of W in a shifted point, T lambda plus rho. Here, by the way, lambda again dominant weight. Okay, we know that the Whittaker functions are supported only on dominant chamber. Okay, and the relation between them is just take a W of T rho, which is an element in COY. Okay, multiplied by the trace. Okay, multiplied by some constant depending on lambda. Okay, and you get the value of W T lambda plus rho. So this means that if we fix the value of T of rho, we fix the whole we fix the function W on all the torus. Okay, so this, as I say, this is the Kasselman-Shalaika formula in the universal setting. Okay. Now let me just say, so the proof basically follows directly from the statement that, as I say, phi lambda plus rho is phi rho times a lambda, okay, and uses the fact that WK is an eigenfunction. So let's see. Basically, starting with a spherical Whittaker function, its value at t and lambda plus rho is nothing but a pairing of the function w with a characteristic function of the coset corresponding to lambda plus rho, just because it is integration of the product. Okay, and now we use the claim in the corollary, moving from phi lambda plus rho to phi rho times a lambda, and by the property of this pairing, we can move a lambda to the other side and get trace out by the fact that WK belongs to this space. So I wouldn't stop here, but as you see, the proof when you follow the notation is basically very cheap. Okay, so as I said, let me summarize so far what we did. We described the space VI as HI model in the linear case and got some nice applications from it.
Can I ask just one?
Sure, please.
Maybe you can remind, does the proof uses the uniqueness of the Whittaker model at this point?
No, it doesn't in any, in fact, it implies uniqueness in a sense. It doesn't. That's one of the nice features of this proof. Okay, now I am going to introduce a new player, which is seemingly not very useful in the linear situation. Okay, it is not really new object. I mean, it has been studied in past, but we are going to use it mostly in the covering case, but it makes sense very well also in the linear case. So let me consider a slightly bigger algebra, meaning algebra that contains the Iwahori-fixed algebra. Precisely, this will be functions on G of compact support, invariant on both sides on some smaller group. And what is this smaller group? It's a pro-P unipotent subgroup of I. Basically, it is, you remember I was, so there is a projection from G of O to G to the finite group G over the finite field. And while I was defined to be the inverse image of the Borel, I1 is defined to be inverse image of U, of the unipotent. So I1 sits inside I, and the quotient is just the torus over the finite field. Okay, if you want to think in terms of matrices, then these are matrices, right, which are modulo P are all unipotent, and on the diagonal they have elements of the form 1 plus P something. Okay, so this algebra was considered by Whittaker some years ago, and then later has been used again by Marie-France Vigneras. And as I say, we shall consider it also in the covering case. So there is pretty similar description of this algebra. So first of all, we have a Iwahori-Matsumoto presentation of this algebra. It is, of course, more complicated than the Iwahori subgroup. But it also contains a Bernstein presentation, which I will describe now. So first of all, let me say a word about the space C of T. Okay, the group algebra. We can break it as a sum of ideals, okay, where each ideal is generated by the idempotent associated to a character. Okay, these characters are of course well, they are complex character, but in fact have their values in the roots of unity of size q minus 1. Okay, that's because this is the order of phi q star. Okay, so those C of chi, please remember them. We'll be using them quite a lot. And now this algebra, which will play, as I say, a significant role in covariant groups, it contains analog of the finite Hecke algebra, which we denote by H0. Okay, these are functions with support on K, and it is isomorphic to the functions by U invariant functions on G, where all the groups are taken over the finite field. Okay, it also has a commutative subalgebra. Let me call it A prime, which it is isomorphic to the space of functions of T mod T1, where T1 is intersection of T with I1. Okay, the intersection of those two is isomorphic to the group of C of T. So precisely the elements of C of chi can be made sense of as an element in H0 in A prime, okay, and we'll be using them. And in particular, actually lying in their intersection. In particular, C of chi can be thought as an element in H. So from now on, H will be this pro-P algebra, while Hi, as I have defined it before, it's an Iwahori-Hecke algebra. Okay, and there is a proposition which is similar to Bernstein presentation as a vector spaces. You have isomorphism of this kind of finite Hecke algebra, okay, and this commutative algebra, and the tensor product over intersection. And again, there are Bernstein's relation which define product on the right hand side. Okay. Okay, so now I still continue. Yeah, so my goal now will be to describe I1 fixed point of the Gelfand-Graev representation. So far before we described I fixed point of Gelfand-Graev representation. So let me now look at I1 fixed point, which is of course a bigger space. And for this, surprisingly, maybe it was a surprise for us, we in fact have to understand the corresponding problem over finite field. So let me describe it. So now all those groups underlined are just groups over finite field. Points over finite field of those groups we've seen before. So we consider the Gelfand-Graev representation over finite field induction. From the character. I remind you that psi was a character with conductor P, and so psi bar is a well-defined character on U over finite field. We take U fixed points, and on this space acts this algebra H0, which we have defined. Now, just by the restriction of functions, this space V0 is isomorphic to the group algebra of on T bar. on the torus. So the idempotent C of chi, where chi is a character on this torus, can be considered just as an element of V0. Okay, so now we are going to describe the space V0 as H0 model. Okay, so remember that C of T bar was written as a sum over characters, as a sum of one-dimensional, of ideals, parameterized by characters. Now let us look on W orbits of those characters. Okay, and inside VO we can break V0 into sum of pieces, summands VO, where every O will be just parameterized, taken as a span over of the idempotence where chi belongs to this orbit. Okay, so first we break this Gelfand-Graev representation into sum on the orbits. Now, how each summand looks like, then we just show, it's a quite simple calculation, that this VO as a H0 module is a induced module, okay, meaning the tensor product over some subalgebra with a one-dimensional representation, okay? The subalgebra, you see what it is, it's averaging of H0 by this idempotent from both sides, and tau is some one-dimensional representation. I can't write it. I can write it. I do not want to write it here because the exact definition involves some Gauss sums. Okay, but still it is some very explicitly defined one-dimensional representation. So let me summarize. We have our V0 breaks into sum over W orbits of characters. Okay, and each piece is just tensor product of H0 with one-dimensional character. Okay, now after we have described the Gelfand-Graev over finite field, let me say get back to the original problem. So we consider the module Gelfand-Graev representation. We look at its I1 fixed vectors, and just the same averaging map as psi gives rise to the following isomorphism. Okay, VI1 is isomorphic to the tensor product as H model. It is just tensor product of H with the space V0 associated to finite Gelfand-Graev over the kind of finite Hecke algebra subalgebra in the pro-P unipotent setting. So I remind that H0 is not HF, right? Because H0 is an analog of HF in the pro-P unipotent algebra. And since V0 breaks into summands over the orbits, so the whole VI1 breaks into the same summands. Okay. Yeah. So this is thus we see that VI1 is a sum of many induced summands of many induced representation parameterized by W orbits on characters. Okay. So now let me just remark that we can recover our previous result. Now we can try and average both sides with I. All right. So far we have defined the I1 fixed vectors, which is a bigger space. Now we want to take a slightly smaller space, I fixed vectors. Okay. And maybe we would expect to have a contribution from those summands, but in fact only one summand in this case survives. The only when we average over I, the only orbit that survives such a crude operation is the trivial orbit. Okay, others just the tensor product just disappears. Okay, so we go back to the original story. Okay, so this is all so far about linear case, and now I'm ready to move to covering case. So please, if you have question about that, it's a appropriate place to ask. Okay, well, if there are none, let me go on with covering groups. Okay, so there is a well-developed theory, probably still not in its final, as I was explained, in final form, but still there is a algebraic theory of covering. They call Brzezinski-Deligne covering. I won't be using much of it, just say that such a covering, Brzezinski-Deligne covering by push-out defines a topological central extension of topological groups, okay, with the center mu n. Now, the unipotent subgroup, any unipotent subgroups in G splits canonically in this covering. And we consider some special covering called tame covering, so that the number n is not divisible by the characteristic of the field. And in this case, there is also a splitting of a maximal unipotent, so the maximal compact subgroup. This splitting is not unique, but we fix it in this talk once and for all. So since there is a splitting of K, it simultaneously gives by restriction splittings of all the subgroups I1, and so on. Okay, now let us define what is the Gelfand-Graev representation. We fix a character embedding of the roots of unity into C star, and the Gelfand-Graev representation will be basically just the same, but now it's not just U psi invariant functions, but they are also genuine functions, meaning when you multiply by mu n, you change it by the character epsilon. And again, we are back to the same question. We want to determine Vi as Hi module, okay? But the structure of Hi is somewhat different than the structure of, in the covering case, than the structure of the Iwahori-Hecke algebra in linear case. So let me say a couple of words about this. So first of all, to define the group G bar, or even back the Brzezinski-Deligne cover, we are required to choose a quadratic form on a co-characters lattice, okay, which we denote by Q, and there is a corresponding bilinear form BQ, okay, and this data defines a so-called modified sublattice of Y, okay, which plays a very important role in the theory of covering groups. So this Y bar is just an intersection of Y with n times the dual lattice of Y with respect to BQ, okay? So this is a sublattice of the same rank, but of finite index. If our extension were just split, I mean, then Y bar would be, in linear case, Y bar is just equals to Y, okay? But in general case, the index of Y in Y bar is bigger than 1, okay? And the algebra Hi contains, first of all, it contains the usual finite Hecke algebra, because K splits, so it should be isomorphism instead, just equality, but because our functions are genuine. So the finite Hecke algebra just as before, but the corresponding commutative algebra is now isomorphic not to C of Y, but rather to C of modified character lattice. It just happens because of genuinity condition that you cannot have functions genuine functions in HI which are supported on the cosets of Y, but not on Y bar. Okay, so again, HI is isomorphic to HF times A as vector spaces, just as before. But the significant point for us is that the map, the Satake map, that twisted map, averaging map that I have talking about before, averaging over U, sending HI to VI, is no longer surjective because elements in VI can be supported on cosets which not belonging to Y but not Y bar. So this hence the algebra HI is less useful in this case, but instead we consider the map S psi to be defined on this bigger algebra, pro-P unipotent algebra. So it becomes handy in this case. Okay. So this is an important difference between the covering case and the linear case. Okay, so again, now we start with trying to write. So now everything is in the setting of covering groups. Okay, we have a Gelfand-Graev representation. We look at I1 fixed vectors. Okay, and want to determine its structure as H module, where H is this pro-P Hecke algebra corresponding to the covering case. Okay, so it turns out that in this case the theorem, the statement is just the same as in the linear group. In S psi again gives rise into is isomorphic to V0, to the induced module, tensor product of H with V0. I remind you that V0 is just the same Gelfand-Graev module for the finite group, okay, and hence, for the finite field, and hence breaks into summands parameterized by W orbits. So I remind that in linear case, when we further averaged both sides over I, only one orbit has survived. So now here the situation is more complicated. In fact, many orbits survive. So let's see which ones. For any weight W, okay, let us fix a certain section, which is not isomorphism because the torus doesn't split from F star to the covering torus. And for each side, using these sections, we can define double equivariant injective map. So let me say what it is. It takes an element in a co-character, okay, and associate to it a character on the finite torus. How it does it? So for every y, phi of y is a character of finite torus. At the element t, we just take a commutator, okay, between y taken the value at the uniformizer and the element t. Okay, the element t can be considered as an element in the covering torus, but remember that the covering torus is not commutative. So the commutator lives in mu n. So in particular, it it defines us a character. Okay, so it is not trivial that this is defined a character. It just depends on the structure of the covering torus, but it's not very difficult to check. Okay, so the claim is that now let's look again at the theorem. You have view I1, which breaks into sum over orbits. If we further average this story over I, we will see only some orbit survives, and which orbits will survive? Exactly those that that appear in the image of this map phi. Okay, so not all the we shall not see all the characters, but only those which appears in Y, and hence actually do very much depend on the covering. So notice that in the theorem, in the first theorem, which was written, it's like uniform. You don't really see the structure of the covering group here, but the map phi definitely reflects the covering. Okay, so we break it into sum over orbits, certain orbits, and we can ask how. Okay, remember that those CO1 is this is a unipotent, this is idempotent corresponding to trivial character. So this is just characteristic function of the Iwahori subgroup. So when we average over I, we make on the right, we make everything, we make each summand to be module over HI. Okay, I should hurry a little bit. Dima, I wonder, so can I extend it a little bit? Because
yes, no problem.
Maybe I'll take another 10 or 15 minutes. Sorry, everybody. Now, so how shall we we want to describe each summand also as a induced model, namely tensor product of HI with some representation. So we couldn't do it in any case, but we could do it in many cases. And let me describe the condition under which we could do it. So this has to do with the combinatorics of the W orbits in this quotient space. So we say that the orbits O in this quotient Y mod Y bar splits if there is a equivariant embedding of the orbit inside Y. Okay, so it's not every orbit's generally split, but if it does, we can take any element in the image and define by WY just to be a stabilizer at this element. Okay, and here is a theorem. The theorem that if orbit splits, then this summand can be written indeed as a tensor product of HI with a character sign of a subalgebra. And this subalgebra, it's in fact a certain subalgebra of the finite Hecke algebra. Okay, it is just generated by elements. I mean, these TW are characteristic functions of cosets. Okay, where W belongs to this stabilizer. Okay, note that this module is a projective model, is a model over HI, which will be useful for the applications. So again, if orbits O splits, okay, then we have a nice description of summand corresponding to O as a tensor product over HI. Okay, so it turns out that this condition, I mean splitting of orbits, holds for, we can describe a pretty large class of coverings for which it holds. So here is a definition. I believe it didn't appear before. The cover is called Ositic. there are so many adjectives corresponding to different type of covers, mostly appearing in the paper of Van Gogh and his co-authors, like saturated and very saturated and aligned and whatnot. So there is another one. It's called Ositic if, well, first n is prime to the determinant of this bilinear form corresponding to Q. So this is some fixed number for every covering. And it also prime to all coefficients of the highest chord. Okay. And here is a very nice theorem that based on results of Sommerson, that if we have an Ositic cover of simple, almost simple, simply connected group, such that for all short roots, the value of Q is 1. This is mostly for convenience. It's not that important. Then every orbit splits. Okay. So what are those Ositic covers? We can actually describe them. The n-fold cover is Ositic. You see, the most difficult condition is for type AR, in this case, n should be prime to r+1, but it is Ositic for all odd n, for classical groups, and for all exceptional groups, the condition is written below. Okay, so quite a lot of condition of groups, of covering groups, depending on n. For a given group, we see many Ositic covers, but there are also non-Ositic. So these examples, if you ever look at those slides again, maybe it's worth to do it carefully, but I will not stay on this slide too much. Just let me give an example that if G is SL2, then if n is either odd or is 2 mod 4, basically non-divisible by 4, okay, then all the non-zero orbits are free, okay, that contains 2 elements, and hence split. Every free orbit, in fact, is split. But if n is divisible by 4, for example, if n is 4, okay, we have lots of free orbits, 0 orbits, and one single non-free orbit, n over 4 alpha, which is singleton, and any singleton orbit which is not 0 doesn't split. Okay, so in this case, we cannot apply our theorem for fourth cover of SL2, for example. Well, I'll skip SL3. I mean, I also describe here the cases of double cover and triple cover. It's not so important now. So if orbit doesn't split, it doesn't mean that there is no description. That we have some expectation that it still has a form of tensor of HI with certain character, but this HY, the algebra over which the tensor product is taken, will no longer be inside HF, but will be stabilizer in the whole affine Weil group, and thus we expect that different maximal compact groups will be involved. So, but I better not comment much about this because we don't have a clear understanding of this case yet. Okay, so now, so let me remind what the main theorem that we have seen. So VI breaks into sum over some subset of orbits, and in some favorable case, when the orbits have splittings, each piece is a tensor product representation HI with a sign over some subalgebra. So now let me talk a little bit on applications of these results. So first of all, I want to mention the paper by Sahi Stockman and Venkataswaran, okay, who, it's a pretty recent paper, maybe about 2 years ago, one or 2 years ago, basically 1 year ago, I think, where they have defined an action of the Iwahori-fixed algebra on the space COY. I remind you that HI doesn't contain naturally the space COY. So the action is quite involved, and they have written formulas for the action of generators. Okay, their motivation was to discover the conceptual reason for Chinta-Gunnells action, on which I will comment in a minute. And the proof is that these formulas for action of generators amount to the action of HI is quite involved. Okay, but we rediscover this action in our work. In fact, this CY can be incarnated as a space VI, where V is a Gelfand-Graev representation, because in fact we can see that VI is a free module over subalgebra A, which is of rank exactly index of Y in Y bar. So it can be, some more words should be said, but it can be identified with C of Y. And just the formulas of action of HI on VI just coincide with, they just match the action of SSV. The localization of their action with respect to some multiplicative system, COY without zero, it recovers the Chinta-Gunnells action of W on the space of rational functions. Okay, and this Chinta-Gunnells action, which was first discovered in terms of determination of local parts of Weil groups of multiple Dirichlet series. I cannot comment anything about that. And it was later involved also in Kasselman-Shalaika formula. Okay, so it's important action. And in the paper of SSV, they give a conceptual explanation why it exists. First, it was proved by using computer that this indeed defines an action. And again, now I think our explanation is maybe even more conceptual in that. But we must say that, in fact, the SSV action was defined on a larger lattice, the co-weight lattice, and we recover only part of it because the co-character of lattice sits inside co-weight lattice, but we expect that other pieces of C of P, which are not COY, other cosets, have to do with Gelfand-Graev representation with respect to characters corresponding to a different conductor. But it's again remains to be seen. Okay, I proceed now to further applications, probably more, quite exciting ones. They are mostly follow from works of Van Gogh, but also uses the results, this decomposition. So let me explain what are those applications. So first of all, we consider the unramified principal series. We start with unramified character of the center of the torus extended to the maximal compact subgroup. There are more than one way to do that, but it doesn't change the result. And we consider it gives rise to the unramified principal series, which we denote by I chi. Okay. Now we consider a space of Whittaker functionals on this I chi, which is can be defined to be home from V to I chi, or home from Vi to the space of I fixed vectors of I chi. In fact, it should be chi inverse, but it doesn't matter very much. Okay, and since Vi, the Gelfand-Graev representation, breaks into sum over the orbits that we considered before, then the Whittaker space also breaks down into some of the pieces parameterized by those orbits. Okay, so each orbit is just home of Hi of this piece, I chi, I fixed vectors of the principal series. And again, if the orbit splits, then this piece is the tensor product of H over Hy with some one-dimensional representation with sign, sorry. Okay, so now here is a problem. For any chi, there is a uniform, for any unramified chi, the dimension of the space of Whittaker functional equals exactly the index of Y bar inside Y. This is a famous failure of multiplicity 1 of Whittaker functions. Now question, if I chi is reducible, okay, so it has many constituents. So unlike in the linear case where only one constituent is generic, here many constituents could be generic, and we are interested what is the dimension of Whittaker space of each of them. Okay, so we address this problem in two cases. One is for regular principal series and for unitary principal series, and actually give a very explicit formula. Okay, so let me start with the application for the regular unramified series. So character is regular if it doesn't have any element in W which stabilizes it. Okay, so we assume that the character is regular, and yet another condition that the set of alpha for which the intertwining operator has a singular point, okay, or if you wish, there is this condition which is written, okay, is contained in the set of simple roots. Okay, if this is the case, then I of chi breaks into, of course, it's not direct sum, but its semi-simplification is direct sum. And by Rodier's result, which are easily generalized to covering groups, they are parameterized by pi s, where s is subset in this phi of chi. So, for example, if we have a character such that phi of chi is delta, this is the case where in linear case the principal series contains a trivial representation as a subquotient. In the covering case, pi delta is so-called theta representation, minimal representation corresponding to chi. Okay. Now I remind that our goal is to define the dimension of the Whittaker space of each pi s. Okay. Let me just remind that since all the modules here, let me say, all those modules were projective module over O, we can say that the sum of those dimensions must be equal. So since they are projective, this functor is exact, and hence the sum of all dimensions of over all O should be equal to the index of Y in Y bar. So here is a result. To compute this dimension, first maybe look at the theorem. Okay, we compute the dimension as a product of characters of two representations of W, okay, which are defined combinatorially. Now, representation sigma is a permutation representation W on this quotient space. which is a union of orbits. So sigma naturally breaks into permutation representation sigma O. Okay. On the other hand, for any S, you have this representation sigma S, which is virtual representation, but eventually gives a concrete. Yeah, well, sigma S is this representation. Okay, and the theorem says that for every splitting orbit, the dimension of the piece corresponding to the orbit O is this product sigma S with sigma O. Okay, hence for Ositic covering, this is exactly the case where every orbit splits. This dimension is the dimension of the Whittaker space of pi S would be the product of sigma S with the permutation representation sigma. So this is the application of our decomposition for regular unramified series. Okay, yet another application, unitary unramified series. Here the story is different, but the answer is given pretty much the same way. So assume that G bar be an Ositic cover of simply connected group, and chi be a unitary unramified character. In this case, the decomposition of principal series is governed by R group, which if chi is unramified, it's a abelian. Okay, this R group is a abelian group sitting inside the while group. Okay, and I of chi just breaks into sum of pi sigma, where sigma corresponds to sigma is a representation of the R group. Okay, so the correspondent is normalized that pi 1 is unramified constituents, and then theorem just computes the dimension of Whittaker space of pi sigma corresponding to O to be the product of the representation sigma O and the representation sigma. So please do not mistake this sigma as a permutation representation which we had in the previous slide. Here sigma is a representation of R chi. Okay, sigma O is in fact representation of W, but can be restricted into to R chi, and this product as two representation of R chi could be reducible, of course, gives a dimension of the Whittaker space corresponding to O. Okay.
So can I ask a question?
Please, yeah, please.
Yeah, just I hope I didn't. So the Whittaker model does depend on an additive character, right?
Yes.
It's not in the notation here, but it does.
Yeah, but my additive character has been fixed. It's all
yes,
has conductor P.
Right, but so these dimensions will not depend on the choice, or if you take a different character of the same conductor, or maybe a different conductor, do you expect these dimensions to vary?
So as far as you do not change conductor, I believe that the dimensions do not vary.
So even for those constituents, not just for the full unramified, I'm asking about the constituents pi sigma.
I think not. Okay, I'd better check. I mean, these results are relatively new. I'm going to. Thanks for asking this question. Maybe I'll check it again, but I believe that it depends only on the conductor. Okay. So, and maybe the last application that I will say about is the Kassaman-Shalaika formula for covering group. So the Kassaman-Shalaika formula, as I said, there is no unique functional of Whittaker functional on every principal series representation. Still, we can define the spherical Whittaker function W. okay, which is cy valued. Basically, we start with the universal principal series, like in the linear case we did before. We can take a normalized spherical vector and take this averaging over OPs over the unipotent against the character, and we get a cy valued function, which is u psi invariant on the left, k invariant on the right. So we are interested to understand what kind of polynomial for any lambda, what's w of t lambda is. So McNamara in his paper quite a long time ago has given a formula for it, which is a bit similar to the formula in the linear case first given by Casimir and Shalaika themselves. So it's kind of alternating sum of action of W on lambda with some coefficients, but the natural action here is replaced by Chinta-Gunnells action, which is very complicated. On the other hand, for linear case, there exists a very simple formula, which I mentioned before. Basically, I have written it in terms of recursive relations. All right. And now I want to speculate that there should be a similar formula in terms of characters of representation of dual group also here, but of course much more involved than in the case of linear groups. So far we have done computation for the case SL2, the even covers. Let me present them here, and this will be the last slide. So we are looking for recursive relations of the Whittaker functional for SL2, which will also reflect the non-uniqueness of the Whittaker model, because to define a Whittaker function, we actually must first define its values in finitely many points. Okay, so we start with nth cover of the cover of degree n of SL2, where n is even. In this case, the character lattice is co-character lattice is generated by a co-root, and y bar by n over 2 of alpha check. Okay, and we have a representation. The dual group is still SL2 if n is even, and the representation ring of it by Satake isomorphism is isomorphic to the co-character lattice. So we, by abuse of notation, write it as a ring of Laurent symmetric Laurent polynomials in x in the power n over 2. Okay, we have W orbit, so y over y bar, which depending on whether n is divisible by 4 or not, it can contain a single orbit or just 0 orbit and 3 orbits. Okay, as usually the representation of SL2 has highest weight representation corresponding to of the dimension L+1, right, corresponding to highest weights. Okay, and we are interested to find the values of the Whittaker functions, well, slightly normalized by this delta minus half t. Don't pay attention on that. So here is a proposition. We look at small k, all k which are representative on y mod y bar orbits. So as you see, k goes between 0 to n over 2. Okay, and when we to define the value of tk shifted by an element of the modified co-character lattice, so you took k and you shifted by a multiple of n over 2, say L times. Okay, and here is the recursive relations in terms of the values of Whittaker functions on the element tk and the element t n over 2 minus k. So why just those? Why not others? Because the elements tk and tn over 2 minus k are exactly the w orbit of tk. Okay, and the coefficients are traces of the corresponding highest weight representation. So we have, as in linear case, trace of this VL. And for the other guy, we have kind of error term, okay, which is trace of smaller representation, and it should contain the constant, which is a Gauss sum. Okay, so this is a fascinating recursive relation for SL2, and we'll be very happy to have something similar in general case, in a sense, to understand how shifting by elements of modified lattice can be expressed in terms of representatives of the given orbits with coefficients from the Hecke algebra. Okay, so to summarize, we definitely have here more questions than answers, but the story that I told shows that those results can be applied to resolve very basic representation in very basic problems in representation theory of covering groups. And I'll finish here. Sorry for going over time. Thank you.
Very nice.
Thank you very much. Questions, please.
So when you said in the general, you expect to have this in the general case, you only mean when the orbit is split, when all orbits are split?
Well, no, there is in case for SL2n, say if n is divisible by 4, in this particular case, we can show that the same proposition holds. So, for example, if n equals 4, we have a non-free orbit, in which case shifted w can be expressed as just trace, just depends just on the value of w on the singleton orbit. But we expect that something like this should be true. And on the right-hand side, you will see values of w on the w orbit of the element kind of tk or t lambda, whatever, in y over y bar. So the combinatorics here plays a very of w orbits of y over y bar plays very significant role in all the story.
Do you have this VI will be a representation of G check in the sense of Weissman, I suppose? So in this case,
there will be, yeah, exactly. It's not VI, it's VL. It's just a, it looks the same though. Yes, this will be just representation of the dual group.
And you have other instances instead of, other than SL2, n-fold couplings of SL2?
Yeah, we are exactly working on this. I have some partial results for SL3. It's not quite clear how to proceed more generally. I mean, it's a long story, but I can share it, not just now and here, but whenever you like.
Nadya, in this formula, can we see some inklings of this Gunnell-Chinta's action? I mean, do you see it here in this page, or it's
no, not at all.
It's not in the page.
No, it is so usually the usual in the linear case, the Kassaman-Shalaika formula is related to the formula using the trace via Weil character formula. In combination of original formula with the Weil character formula gives us a trace. So I don't know. I will be happy to see that if there is some kind of deformed Weil character formula, but I really don't know exactly what happens here. It's just my feeling is that such a nice formula for SL2 couldn't be just instance of SL2.
Thank you very much.
Well, thank you all for coming.
Thank you very much again. So we have a speaker in 2 weeks. Let me, it's Tasho Kaletha.
Oh, cool.
I don't have a topic yet. I'll send one.